All right. So this one is pulley advantage and then an Atwood machine involving pulley advantage. Um, so first we do it when that thing's at rest, and then I guess I'll just do it with one of the accelerations of the elevator. Um, okay, so for part A, we're going to assume that um, the elevator isn't accelerating. And remember that what matters here is the acceleration of the reference frame. So if this thing is moving with a constant velocity, everything would be the same as if it's at rest. Um, all right, so I'm going to do a free body diagram of the 20. Actually, just for setting up the equations, I'm going to do the 40 first. We have to do both of them anyways. So we have the weight down of 390, 392.4. And then we have a cable force up. And so Newton's second law says 0t plus 0 negative 392.4 is equal to the mass times the acceleration. And we're just going to assume all this stuff is just going straight up and down. There's no acceleration side to side. I'm just going to call this 0a. Okay, so if we get a positive number, it means the 40 kilogram mass is accelerating up. If we get a negative, it means it's accelerating down. And we get one equation here that says T minus 40A is equal to 392.4. And we can't solve that because that's two variables, one equation. That's right. And then now I'll go to free body diagram of the 20. And I'm going to do everything that's hanging there. So my free body diagram is going to be kind of like this. So I'm including a little bit of the cable that goes underneath that hanging pulley, and I'm including all the hanging stuff. Okay. So we got this with the little bat ears. We're assuming the pulley is massless, the cable is massless. So the total weight here is 20 times 9.81. So 196.2. And then the cable is the same cable, so it pulls on, the excluded part of the cable pulls on the included part an amount T here, and it pulls on an amount T here. So we have 0T plus 0T plus 0, negative 196.2 is equal to 20 times the acceleration. And now we have to think about the relationships between these motions. So if the 40 kilogram mass goes up 1 inch, how much does the 20 kilogram mass go down? What? Half. Yep, exactly. So if we call this one 0 positive A, we have to call the other one 0 negative 0.5A. Okay, that's just a geometric requirement between those two. So this is 0 negative 0.5A. And we get the second equation that says 2T plus 10A is equal to 196.2. And now we have our system of two equations. And then A, the variable A, is negative 6.54. Okay. And now we're going to go to what happens when the elevator is accelerating.
I have a question.
Yeah.
If the acceleration is negative when we are calculating the acceleration for the 20 kilograms, but we getting positive because we got minus.
Exactly. So remember that you already have it all laid out in front of you. You just didn't know what a few like parameters defining it are. So the acceleration of the 40 kilogram, now all you do is plug that A value in here and you have it. The acceleration of the 20, all you have to do is plug the A in there. Okay. And it's that way for force vectors acting on things too. Like, for example, we know this is the force applied to the body by the cable. We just didn't know what T was yet. Now we do, and you just plug it in. Okay, so now we're gonna, well, let's write this vector. Let me check what it asked for. Okay, hold on, my computer's thinking for a second. What's the acceleration of the 20 kilogram mass? Okay, so the acceleration of the 20 kilogram mass is 0, negative 0.5 a. So that is 0, negative 3.27. And now I'm going to assume the elevator is accelerating up at 2 meters per second.
Isn't it positive?
Yes, that's what we just talked about. You're right. It is positive. Thank you. Thank you. Now the elevator accelerates up at 2 meters per second squared. Okay, so we got to do this calculation over again. So think about the thing with so these accelerations have the same effect as a gravitational field. Do you expect the tension and the acceleration to get bigger when this accelerates up or get smaller?
Bigger?
Yeah, they're both going to get bigger. Yeah. So it's like increasing the gravity. So I'll start with a free body diagram. Oh, and the basic idea here is going to be that the acceleration of either object, I'll call them masses, relative to the ground, is equal to the acceleration of the mass relative to the elevator plus the acceleration of the elevator relative to the ground. And this is the one that's just going to be 0, 2. And this is the one that we're going to try to calculate the acceleration relative to the elevator, like what an observer inside the elevator would see. So this is what we want. So free body diagram of the 40 first. The free body diagram looks the same. So we have 392.4 down. And then we have our cable force up. And the acceleration that we want is relative to the ground. So this is going to be equal to the acceleration of the mass relative to the elevator plus 0, 2. That's the acceleration of the elevator relative to the ground. And so I'm going to write this as 0a plus 0, 2. Okay, so for an observer in the elevator, we're still just we're assuming the acceleration of the 40 is 0a, and we'll just calculate what that a is. But in a ground frame, you have to add on the acceleration of the elevator. So now Newton's second law says 0t plus 0, negative 392.4 is equal to the mass times the acceleration, which is 0a plus 2. And so the equation, if I move this stuff around, we have t minus 40a is equal to 392.4 plus 80, so 472.4. Everyone with me on that? And now we'll go to the 20. Excuse me. So, okay, we'll take everything that's hanging, including a little bit of cable going under the pulley. And so the weight is 196.2. The only other external loads are a cable force here and a cable force here. The acceleration this time, it's going to be the acceleration of the mass relative to the elevator plus the acceleration of the elevator relative to the ground, which is this. The acceleration of the mass relative to the elevator has to follow that geometric requirement, the way the cable works. So this is going to be 0, negative 0.5a plus 0.02. And so Newton's second law says 0t plus 0t plus 0, negative 196.2 is equal to 20 times 0, negative 0.5a plus 2. So the equation that's useful to us is 2t plus 10a is equal to positive 196.2 plus 40. So that is 236.2. And notice that what you have here is the left side of the equations look the same as they did here. But the right sides that kind of represent the applied forces that have to do with the weights, those are both increased as if the gravitational force increased. And so now start solve. And we got the T was equal to 157.47, a little bigger than it was before. And A was equal to negative 7.87 meters per second squared. And so the acceleration of the 20 relative to the elevator is 0, negative 0.5 times this. So that is 0, 3.94 about. So bigger acceleration. Yep.
So I know that tension always would be positive, but for the acceleration, would it always be negative?
Nope. It just has to do with, if I would have said at the start that we're going to assume that, if when I did the free body diagram of the 40, I could have assumed that it was going down and called this 0 negative A, and then we would have gotten a positive answer for A. But the sign will just always work out, so you don't have to think about it. You can just always take your first body, assume that, call that 0A, figure out the acceleration of the second body based on that, and it'll work out with the signs. Any other questions? Okay, so now 14. So we have a 5 kilogram object moving in spherical motion with a radius of 2. We've done more circular motion than spherical, but mathematically all it does is just, it works all the same. It's just the cross products can have more than one non-zero component. It has a constant angular acceleration, and at the time 0, its angular velocity is this.
Can you make that a little bigger? I can't read it.
Mm-hmm. Just erase this. Go back here. Okay, so we're given the constant angular acceleration, and at time 5 seconds, we're given an r vector. Okay, and so we're gonna use some definitions of relationships between angular velocity and angular acceleration. Remember that the angular acceleration vector, you can think of its definition is the time derivative of the angular velocity. Okay, so we can think d dt of omega as a function of time is equal to 0 for negative 8. Okay. And we're going to need to know the angular velocity to do these calculations because they come into the watermelon equation. And so we're going to have to do these differential equations to find omega as a function of time. So I'll start out with d omega x dt is equal to 0. So d omega x is equal to 0 dt. You can integrate both sides. And omega x is just equal to the constant of integration. And then we'll use the boundary condition. So the boundary condition says when time is equal to 5 seconds, oh, no, yeah, it's a different one. When time is equal to 0, the angular velocity is 5, 0, 0. So we have that omega x is equal to 5, and that's equal to c, so omega x as a function of time is just equal to 5, so that doesn't go anywhere. Well, it goes somewhere. It doesn't, the angular velocity component doesn't change. And then we have d omega y dt is equal to 4. So d omega y is equal to 4 dt. Integrate both sides, and you get that omega y component as a function of time is equal to 4t plus c, a new c. And then the boundary condition says when time is equal to 0, omega y is equal to 0. So we have 4 times 0 plus c is equal to 0. So c is equal to 0. So omega y as a function of time is just equal to 4t. So we have this one. We have this one. And now we'll do it for z. D omega z dt is equal to -8. So d omega z is equal to -8 dt. We can integrate both sides. And omega z as a function of time is equal to -8t plus a constant of integration. The boundary condition says when time is equal to 0, omega z is equal to 0. So -8 times 0 plus c is equal to 0. So c is equal to 0. And therefore, omega z as a function of time is equal to -8t. So all together now, we have omega as a vector as a function of time is equal to 5, 4t, -8t. And okay, so that's the first thing it asks. That angular velocity is a function of time. We have that. Velocity vector at 5 seconds, acceleration vector at 5 seconds, and the net force at 5 seconds. All right, so the velocity vector, bless you, is equal to omega cross r. So we have to figure out what omega and r are at time equals 5 seconds. So omega is equal to 5, 20, -40. Just plugging 5 seconds into the function. and R come on now. Okay, at 5 seconds, the vector from the center of the circle, the sphere really, to the object is 0, 0, 2. So since that's the center of the spherical motion, this is our R vector. So 0, 0, 2, just at this instant. And so the velocity vector is 5, 20, negative 40, crossed with 0, 0, 2. So that is 40. And then negative 10. And then 0. Any questions about that part? And this is also omega cross R, so we can use this in the next part when we calculate the acceleration. The acceleration is the watermelon equation. All ripe watermelons will rot. And we can use this here. And we already have R and we already have omega at time 5 seconds. Alpha was the thing that's given, 0, 4, negative 8. R is 0, 0, 2. Omega is 5, 20, negative 40. We'll substitute in the omega cross R, which is 40, negative 10, 0. And I didn't get anything. I got a syntax error. Let's see. Oh, I see. I got negative 392, negative 1600, and negative 850. And then the last thing it asks is a net force. Well, if you know the acceleration and you know the mass, you can always just multiply those together for the net force. This is 5 kilograms. So Newton's second law says F net is equal to 5 times the acceleration, which is negative 1960, negative 8,000, negative 4250 newtons. Any questions about that? Okay. Any other homework questions? Okay, well now we're moving on to the next topic. And if I had to pick one topic in this class to call the main, like sort of the heart of the class, I would say it's this. We're moving on to rigid body kinetics. And so the way that you derive the stuff for rigid bodies, and rigid bodies like you would imagine, we're just going to, every calculation we do in physics and engineering is an approximation in some way. The approximation we're making here is that these objects don't deform over time. Okay, so everything deforms as time goes by, but some things do it very little, and we can get a lot of useful information out of this calculation. The way that you do the derivation, so Isaac Newton didn't do any rigid body stuff. He just came up with F equals ma and applied it to particles. But if you apply F equals ma to a bunch of particles, you can figure out some stuff about how collections of particles work. And then if you assume that the relationships between those particles don't change over time, that the thing is rigid, you can figure out a lot more useful stuff. So the intermediate step in going from Newton's second law and Newton's third law to rigid bodies is to first just think about general collections of particles. So I'm going to call that like the intermediate step. So general collections of particles. And so this could be rigid bodies, or it could be a glob of pudding, or it could be a bunch of marbles. It's just any collection of particles. And so the question is, can you say anything useful about this? I mean, it's such a general thing. We're assuming so little. Is there anything useful you can say about collections of particles? So can you say anything useful that comes from Newton's laws?
Every force there's an equal and opposite reaction in
Yeah, that still holds. So surprisingly, there is one thing that comes up all the time, no matter how the particles relate to each other. Newton's second law says this. The net external force on a system of particles is equal to the total mass of the collection of particles times the acceleration of the collection center of mass. Okay, this is amazingly useful. I don't usually, I talked about this a little before, the fact that we're only concerned with external forces. I'm going to put it in here now explicitly for collections of particles, because I want to point out that if you think of a collection of particles as like a bunch of marbles bouncing around, this is excluding all the forces of two of those marbles bouncing into each other. Okay, so all we care about is outside stuff applying forces to the system. So let me give you an example to show what this means. So let's say that there are 51 kilogram balls deep in outer space. So there's no gravity or anything. And let's say that you apply a 20 Newton force to one ball. What's the acceleration? And let's give this a direction. So I'll just do it like that. So I'm going to call it a y component. But what's the acceleration of the center of mass of the 50 balls. Okay. So each ball, its center of mass is at the center of the ball, but you could calculate the center of mass of the whole group. And when you apply this force, what can we say about the acceleration of the center of mass? Yeah.
I just had a question. In this example, is this the situation where the relative distance between all of the balls stay constant, or is it like the putting work and like?
No, yeah, we don't. It's amazing how much stuff this covers. So these balls could be 50 miles apart from each other, or they could be touching each other like a pool break. Okay. But no matter which one of those cases we have, or two could be touching and the rest could be separate or whatever. But the answer is the same in all of these cases for the acceleration of the center of mass. At first, when you think about it, it doesn't really seem possible. But then you're like, okay, well, if they're not touching, then hitting the one ball isn't going to affect the other ones at all. But you're going to get a big acceleration of the one ball. Okay. If they're all together, hitting the one ball is going to affect all of them, but the acceleration of each one is going to be much smaller because of those internal forces. Okay. And so, yeah, so let's see. So Newton's second law says we have a net external force of 0.20, and that's equal to 50 times the acceleration of the center of mass. And so just divide it, and yeah, 0.4. So the acceleration vector of the center of mass is 0, positive 0.4. If you just hit one and they weren't touching? Yeah, exactly. So notice we didn't even have to know if they touch each other. That's amazing. Okay, so like think about a person jumping up into the air. Like say that you had it was gym class, and you're told to try to get your center of mass of your body as high above the ground as you can. So you jump as high as you can. Is there anything you can do at that point once you've left the ground to raise your center of mass? Like you might think, okay, I'm going to pull my knees up to my chest. I'm going to lift my hands over my head. That'll raise my center of mass up my body. It will do that. But this says that once you're off the ground and you've applied all the forces you can until you get off the ground. And once you're off the ground, no matter what you do to adjust where your center of mass is, the acceleration is it's just free fall, and there's nothing you can do, you know?
What about like pole jumpers? How they?
Yeah, so like in track events and stuff, people do all this crazy stuff, positioning their body. You see the long jumpers like twirl their arms or whatever. You see the high jumpers go over the bar backwards and stuff. All they're doing is trying to get their body in a favorable position. Well, the long jumpers are trying to get in a favorable position to land, so they can get their body out as far as possible. But their center of mass they can't control. Their center of mass is just a projectile when they leave the ground. Same thing with the pole vaulters. I mean, they're just trying to get and the high jumpers, they're just trying to get their body in a position so that their center of mass they can't control, but they can affect how their body relates to the center of mass. And in fact, I don't know about pole vault specifically. I would guess it's the same, but I know in high jump, a good high jumper who's getting close to the highest bar that they can clear, this sounds amazing. but they actually get their entire body over the bar, and their center of mass will never reach the height of the bar. Yeah, isn't that amazing? They just keep so yeah, at every instant, if you calculate where their center of mass is, they're sneaking part of their body over the bar, but their center of mass is below the bar. And so, in like, I think 1968, like this American high jumper revolutionized the high jump by doing the weird looking backwards thing, the Fosbury flop. They used to do a thing where they'd run and sort of go over it sideways. But the big advantage of the Fosbury flop is that your center of mass can get way below the bar. When you're doing that roll, the old roll technique, you basically have to get your center of mass over the bar. And so you need to be able to jump a lot higher to clear the same height. Okay, well, is there any, can we say anything else about it? Going back to just general collections of particles. There's one more thing we can say. It's not usually that helpful, but sometimes it is. We're not going to use it in this class, but this is the version of the moment equation that's useful in this case. So I'm going to call this rotational Newton's second law. That's going to be the moment equation for us in this class. That is to rotational Newton's second law. And I'm going to abbreviate that Rn to L. That's going to eventually be the moment equation. But if you so I'm going to define capital H sub A as a vector is equal to a row vector that goes from the about point crossed with the velocity vector. And this is called the angular velocity. About that point A. And rotational Newton's second law says if you take all the external moments applied about that point A, so many subscripts, and add them all up so you get the net. This is equal to, for each individual particle, the sum for each individual particle from I to, say you have n of these particles, of the time derivative. I'll write it like this. Come on now. So it's equal to the time derivative of each one of these angular velocities. And you could also write it as the sum for each one of these particles of the row vector for that particle crossed with the mass. Oh, I wrote this wrong, sorry. This should be mv. It's a momentum, so that makes sense. And so this is rho sub I crossed with mi times vi, and then the time derivative of all of that. And what about this A? There's only two possibilities for A where this holds. So A has to either be the center of mass of the system, or a point that's fixed in the inertial coordinate system. Okay, if your point A is not one of these two, that equation doesn't work. All right, this is occasionally helpful, not usually though, because in the general case, you'd have to be calculating this moment for each one of these particles. But this thing is going to turn into something super useful when we arrange these particles as a rigid body. Yeah. So what it means is, so a rigid body is if you have n particles that make up a rigid body, okay, then you could have a coordinate system that's fixed to that rigid body, okay, that moves around with the rigid body. And according to that coordinate system, the location of every particle stays the same. So let me interpret that, do an interpretive dance of this. So, okay, so say there's a coordinate system that's fixed to my foot, you know, and right now in this snapshot, that coordinate system says my hand is, you know, whatever directions it is. It says it has some vector. My other hand has some vector. My head, you know, has some vector. So it has vectors describing every point, and there can be infinitely many of those points. And now I could like do cartwheel. If I stay rigid, no matter as I cartwheel around or whatever, that coordinate system would still see the exact same vector for my hand, my other hand, you know. So that's what it means. So now we get to the big one. If all the particles are arranged into, I'm just going to say a rigid body, you know, I think really that's the best way to think of it. It's just something that doesn't bend, doesn't, you know, the shape doesn't change. Then what we have is this. So Newton's second law, first of all, says F net is equal to m times the acceleration of the center of mass. And rotational Newton's second law says that m, the moment about A, net, is equal to the mass moment of inertia about A times the angular acceleration vector. And we have, yes, question?
I was wondering what the rho vector is representing.
Okay, yeah. So that rho vector came up in statics when you were calculating moments. It's the vector that goes from the about point. Not everyone in this class took statics, but it's a vector that goes. So first of all, you don't need to know this for this class. This is just kind of in your notes, whatever. It's just a little background. We're not going to use this equation, but it's a vector that goes from the about point, so from that point A to the particle of interest.
So it is a moment then?
No, it's used in calculating moments, but we'll get into that probably next class, I think. Okay, so just like there were restrictions on what the about point could be for this crazy looking equation, we have the same restrictions on what the about point can be. So this is true where A is either the center of mass of the rigid body, or a point on the rigid body that's fixed in the inertial coordinate system. Okay, so an example of that, like what's a point that's on a body that's fixed in an inertial coordinate system? An example would be like a hinge. You know, at the hinge point, that part of the body can't go anywhere relative to our coordinate system. Not all problems deal with things that have a fixed point like that. And if there's no fixed point like a hinge, then you have to use the center of mass. If there is a hinge, though, it saves you a little work. So it's best to use it if possible. Okay, so this is what we're going to be trying to make sense out of over the next week or whatever. And I want to say a little bit about 2 and 3 dimensions. So first of all, Newton's second law. If you're in 2D, this gives 2 equations. If you're in 3D, this gives 3 equations. Rotational Newton's second law. In 2D, this gives 1 equation. And in 3D, the people who took statics with me, the most likely guess would be that this gives 3 equations. But this is something important to remember. This approach that we're using does not really work for 3D. We kind of need a new way of doing things for 3D. So we have to use a totally different approach here. And I'll mention this briefly at the end of the class, how this would go, but okay, well, so these are the equations we're going to use, and we're going to do pretty much all of our calculations in 2D regarding this. So we'll use this in 2D. And if you look at these, there are a few things that we have to define before we can start using this equation. So before we can use this, we need to define the first one is the center of mass. And we're going to do that in terms of the centroid, and we'll talk about when those are the same thing, when they're different things. The second one is the mass moment of inertia about a point. And because this is so important to us and such a mouthful to say, people leave off the mass and they leave off the about a point. But these things are important to remember. The moment of inertia is not defined until you choose a point to calculate it about, and that there are other moments of inertia other than the one just for mass. In fact, the people who are taking deform right now, so this, we're going to always call this I sub A, capital I sub A. In deform, pretty soon we're going to have a moment of inertia that we're also going to call capital I sub A. And it also has a parallel axis theorem and all this stuff that we're going to use here, but it's a completely different thing. It's an area moment of inertia. So don't get confused with those two. And then the last thing is the moment of a force about a point. That's going to be our capital M sub A. And again, since we use this all the time, people tend to just leave this off and call it a moment. But the fact that it has to be caused by a force and that it has to have a defined about point to make sense, you should keep that in mind. In physics, depending on who taught physics to you, it's very likely that you called this a torque or interchangeably used moment and torque. Physicists call they're interchangeable for physics people. Engineers have a specific meaning for a torque. A torque is a pair of equal and opposite couples so for engineers, we always call this a moment. Okay. And that's because we're reserving the term torque for something else. Okay. Okay, so we're going to start by defining the center of mass. And so if a body is homogeneous, and homogeneous means the same material all the way through. So like a sugar cookie is homogeneous. Everywhere you go in a sugar cookie, you pick out a piece, it's a piece of cookie. A chocolate chip cookie is not homogeneous because sometimes you go and pick out a piece and it's cookie, sometimes you go and it's chocolate. Okay, so as long as it's consistent all the way through, consistent material all the way through, the center of mass is the centroid. And the centroid is the geometric center of the material of the body.
Well, we have examples where the centroid is not the center of mass, where there is a change in.
Not in this class, we're not going to. We'll talk about the sum formula for centroids, and you'd use kind of a similar sum formula if you had something like that. So as long as the body's homogeneous, we're only worried about the centroid, and this is the definition of the centroid. It's an integral definition. And we have separate ones for 2D and 3D. In 2D, x bar, y bar, so those are the coordinates of the centroid in your coordinate system, is equal to 1 over the total area of the body times the integral over the area of x, y, dA. And these are the coordinates of the centroid of the infinitesimal area dA. In 3D, it looks similar. You basically just change the areas to volumes. But X bar, Y bar, Z bar is equal to 1 over the total volume times the integral over the volume of the body of X, Y, Z times dV. And X, Y, Z in the integral are the coordinates of the centroid of that infinitesimal volume dV. Well, let's try this. So let's think of, this is doing something on the fly like this is always a bad idea, but let's see if we can get through this. Yeah. So let's figure out the centroid if the coordinate system, if the origin is here. And let's say that this is y equals x squared. And we want to find the centroid of the shaded region. Okay. So I am going to, if you look at this definition, it's all in terms of these infinitesimal areas dA. And the way that you set up your infinitesimal areas is kind of determines whether it's possible to do or not. I'm going to choose my infinitesimal areas like this, like when you first saw the definition of the integral. Okay, so that's my dA. And my total area we can get by integrating this. So we're going to need that. So this is the integral. Oh, I didn't give boundaries. Let's say this is 1. So this is 1. So we have 0 to 1 of x squared dx. That'll give us the area. And so we got x cubed over 3 integrated from 0 to 1. And so that's point. No, it's not. Okay. So that's our A total. And now we're going to use the definition and think about this shaded region here. So x bar y bar is equal to 1 over 3. So I'll just write it like this for now, but that's obviously 3. And now we're going to take the area, the integral, I mean, where, so let's think about one of these dAs. What would be the centroid location of this shaded red rectangle? Yeah, so it would be, so it's infinitesimally thin, so our x location is just going to be x. And then our y location exactly is going to be 1/2 of the height. The height is x squared, so it's going to be x squared over 2. So this is just going to be x squared over 2. And we're doing it in terms of x, and our boundaries are 0 to 1.
How do you get x to the power of 0?
Because this is defined by the function y equals x squared. So y is equal to x squared at the top of the rectangle, but the center of the rectangle is halfway up the rectangle. So that's why I divided by 2. And so now we have 3 times x squared over 2 here, x cubed over 6 here. And we're evaluating this. Oh, I didn't put in the area yet. So we still need to multiply by this dA. Okay. So what's dA for this thing? Well, it's a rectangle, so it's just going to be the width times the height. The height is x squared, the height of that red rectangle. The width is dx. So I left off this x squared here. And so now we have 3 times x cubed, and this is x to the 4th over 2. We're integrating from 0 to 1 dx. And so this is 3 times x to the 4th over 4, x to the 5th over 10, evaluated from 0 to 1. And so x bar, y bar is equal to 3/4 for x and 1/10 for y. Wow, that came out so nice and clean. 3/10, yeah. And so if you draw this shape, like this, it's going to be over here somewhere, and it's going to be like over here, and so the centroid is there. Okay.
Is that the specific notation you use for a centroid? The circle with like the
Yeah, that's the symbol for center of mass. Okay. That's why when I was a kid, for some reason, every car commercial featured crash test dummies in it. They were, and in the crash test dummies, they have those symbols all over their bodies. They have one on their upper arm, lower arm, on their head, and all those things are because in doing dynamics, you can see the center of mass is this really important thing. So if they're trying to do physics based on high-speed videos of crashes or whatever, they need to know where the center of masses are of all these body parts. And so that's what that means.
Would a circle with an X on it also work?
I have never seen that. It would certainly work if you know what it is, but it wouldn't work, I guess, for communicating with other people, I don't think. Okay, well, it would be best if we didn't have to compute integrals like this every time we wanted to use a mass moment of inertia. Anytime we wanted to use a centroid, I mean. 3 things work together so that we rarely have to use this integral definition. The first one is the centroid always lies on any line or plane of symmetry. So the more symmetric a shape is, the more of the centroid location is already defined for you. You can think like, what's the most symmetric shape you can think of? A sphere. And so because of all that symmetry, every plane of symmetry of a sphere intersects at the center of the sphere. And so the centroid of the shape, the center of mass of the shape, is just the center. A line would be if you're working in 2D, and a plane would be if you're working in 3D.
Would it be something like a cone?
Then you have the second thing is once someone uses the integral definition once for a given shape, they'll come up with an algebraic formula for it, and then you can just use the algebraic formula. And so in practice in this class, I'm just going to give you the centroid formulas for the shapes that we need, like a right triangle, a quarter circle. I think those are the only two that we really need. I didn't get an algebraic formula when I did this because I didn't define it in terms of parameters, but you can imagine that I could have made this more general and said y is equal to, like, say, ax squared plus b. And then we would have gotten our answers in terms of a and b. And then anyone who came after us could just use the formula that we got in terms of a and b. And then the third thing is if you can break a more complicated shape up into a collection of simple shapes that we know the centroid for, you can use a sum formula. And so we don't have time to get into these right now, but on Wednesday we'll go through all of these. And I can't remember. I might make you do one integral definition calculation, but if I do, it's the only time you'll have to do it all semester, and it's probably for a right triangle. Okay, any questions? That's all.